Okay, so we talked before, actually a couple conversations ago, we said we were going to talk about the characteristics of an NMR spectrum. We talked just recently now about the number of signals. Where am I here? We talked about the number of signals. We gave a couple conversations about that. They're sort of a simple, and that's the number of kinds of hydrogens, right? There's a simple version of that and a detailed version of it, all right? I'm only going to give one conversation about the location, and it's a little complicated, but we're going to take some time with it and hopefully get something very useful and very simple out of it. So by location, I'm saying that this, right, can you see that that is about 1.2? That has a signal at 1.2. Here's a signal that, say, looks like 2.6, and here's a signal at maybe 7.2, right? You see that signal? Okay, so we got three signals here, and they're at different locations, and they indicate the electronic environment of each of these kinds of hydrogens. All right, so let's look at this more specifically now. I'm going to get a little bit of details here for you, and then we'll hopefully bring this in and be super simple. So in many NMR solvents, the solvents that we use to dissolve the analytes, we put about 1% of TMS in it, tetramethylsilane, and we do that because the frequency of these protons is less than most organic solvents, so we can use it as sort of a baseline. We call this 0, all right? So we'll set that at 0. There will be a little signal here for TMS, and we'll put that signal at 0, okay? Now the shift for any proton signal, right, is calculated as a comparison relative to the TMS, okay? So the observed shift is calculated like this. The observed shift from TMS is divided by the observed shift from TMS divided by the operating frequency of the instrument in hertz, okay? So for example, we might have a difference of 2181 hertz between the proton that you're looking at, 2181 between that and TMS, and then we'll divide that by the frequency. This would be a 300 megahertz machine, and we'll say this will be our chemical shift, and oftentimes we'll say 7.27 ppm, parts per million. That's what that is, okay? 7.27 parts per million. I don't think this is hugely important. I just want you to see where that stuff comes from, and you won't be doing any calculations, but yeah, it definitely comes from someplace, and if it really mattered to your understanding, you would practice this, and you would get it. It's easily within reach of the kinds of things that you can do. So that's how we get where the chemical shift comes from, all right? So the shift, we say ppm, but the shift relative to TMS is a dimensionless number, so we call it ppm. And most signals for hydrogens occur between 0 and 10 ppm, okay? Most proton signals appear between 0 and 10 ppm. We'll get used to that. All right, and then just to give you a little background on how these things work, current NMR apparatus analyze samples at a constant field strength over a range of energies. I'm not sure that that's really super important to you, but to give you a little bit of background color. Shielded protons now, that's protons that are shielded by electrons, have a smaller magnetic force acting on them. Shielded protons have a smaller magnetic force acting on them, so they have smaller energy gaps and absorb lower energy radio waves, okay? So a shielded proton, you don't even really have to understand what a shielded proton is, I don't think, but I will say that methyl groups are shielded, and things that have electronegative groups next to them are de-shielded. So you see a little bump right there, there's something going on there. But something comes downstream because it's de-shielded, all right? Again, that's not super important other than to say there is a reason why these guys show up downfield. Okay, alkanes, that is, look at this. An alkane generally has signals around 1 to 2 ppm. So if it's just plain methane, it's going to be really close to 1 ppm. If it's got an electron withdrawing group on it, it's going to be shifted downfield a good bit, okay? More electronegative element, further downfield, right? More electronegative element yet, thank you, further downfield, and more electronegative element yet, way downfield, right? So watch out. You can't just say because it's a methyl group that it's going to be at 1. It sort of depends on what it's around, right? So, and I guess to show even further, if you've got 2 electron withdrawing groups on a methylene carbon, then it's going to be further downfield. And then, if you've got 3, it's going to be way downfield. Okay? So, and the idea of induction also, this is induction here, right? The idea, the proximity of induction also matters. So the hydrogens that are right next to the chlorine are going to be shifted, but the ones that are further away are going to be shifted less. You see that 1.6. And the ones that are gamma to the chlorine are going to be essentially unshifted. Where are we now? Let's go on. Okay. So to predict chemical shifts, we want to predict some. We start with the standard ppm for the type of proton, and then we consider what's around it. All right, so a methylene is going to be at what, 1.2, everything else being equal, and a methine, if there's just 1 hydrogen on it, it's going to be about 1.7, everything else being equal, and then we'll refer to a table to adjust ppm depending on proximity and certain functions. Okay, so let's look at table. Let's look at table 15.1, and that previous slide said 16.1. So if an oxygen is next to it, you see an oxygen next to these 2 hydrogens, they're going to be shifted down a good bit, right? 3.7. And if you see an acetyl group next to a methylene group, it can be shifted down even further, right? You see the acetyl group here? It's shifted down even further. So the effect of beta protons is about 1/5 the effect on alpha protons. That means if you're talking about these guys, right, these are alpha to the group and these are beta, the effect is going to be about 1/5 of that, which becomes negligible, right? So instead of adding 2.5, you might add 0.5, and you might expect something that's 2 away from an oxygen to be 1.7 instead of 3.7. All right. So we're going to be using handbooks and tables a lot to be comparing these, and I don't think I want to go into that example right there. I do want to point out one more thing, though. There is something called diamagnetic anisotropy, and we don't need the term, but I want to explain why when we have a benzene ring, things seem a little bit weird. It turns out that there's a deshielding because of an induced magnetic field. So there's a ring of electrons on top and below this plane because of the pi bonds, and that gives a very unusual place for, gives a very unusual character to hydrogens that are on a benzene ring. Because of, I don't want to say anything about that. Let's move on. So if you have, look at this, hydrogens on a benzene ring, you see that? They're way downfield. Look at, they're down here at 7.2, right? And that's because of diamagnetic anisotropy. All right? So again, you don't have to know the term, but just do be advised. There is a reason why these guys are way downfield. There's no electronegative atom on here, and it's not polar, but it's still very deshielded. Okay? So it's way down there. This is super characteristic. Matter of fact, earlier in a previous conversation, I looked at this spectrum. I didn't even see this here, and I knew immediately because this was down here in this region. I knew it was hydrogens on a benzene ring, right? Because your eyes are just going to get used to it, and you'll immediately recognize it. Okay. However, watch out now. Not everything that looks like this sort of looks like a benzene ring too, right? But since these guys are on the inside of the ring, they're actually shielded. Okay. And so their ppm is -1. So just got to watch out for that. You're gonna have to train your eyes to differentiate stuff relatively easily. It won't be difficult for you, but do be advised. These still are at 8 ppm, and these are at -1. So these hydrogens are very different than the ones on the outside of the ring, and that is because of diamagnetic anisotropy. All right. So in final, we're going to look at. We're going to be reviewing or referring to this table frequently. So if you have methyls, they're going to be about 1. Methylenes, a little higher. Methynes, a little higher yet. Allylics, you see how that's like 1 away from a double bond. That's about 2. Alkynyls, right? You don't even need to know the names. Just get used to this. If you've got a triple bond and a hydrogen that's on that very carbon, it's going to be about 2.5. Aromatic methyls, that is a methyl group that's on an aromatic ring, is going to be about 2.5. We're going to use this over and over and over again, and it's going to become quite familiar to you. So here's interesting. Look at this. That's actually on the aromatic ring. It's real easy to get these two confused. Can you see the difference? One is not on the ring, but it's next to it, and that's at 2.5. But if it's actually on the ring, it's between 7 and 8. You see that? And alcohols, wide range, 1 to 4, some textbooks will say. All right, so we're going to use this table frequently, and it's going to give us a great deal of information about chemical shift. I'm going to demonstrate for you a little bit later how I'm going to organize my notes when I'm making things like this. But for now, this is the information I need to organize in my head as I'm moving along. Hope that's helpful.